Okay. Yeah. So hello, everyone. Yeah. So I thought that we have to consider some examples. Yeah. Some examples. So you probably know how to construct a quadratic extension of a field, yeah? Do you? Yes, square root. Well, more or less, yeah, because there are some subtleties like characteristic 2. So quadratic, yeah, so maybe let me write this. Quadratic extensions. Quadratic extensions, so just add the square root of something. So, and this is, I mean, this is good if so it is a Galois extension if characteristic is not 2. But well, but also you can so in characteristic 2 there are other extensions. You know this Arten-Schreier, when you add well, maybe in I don't know how it, so so k of b, where b squared minus b is something, yeah, like a in okay, yeah. So with quadratic it's easy. So quadratic. So what is good about this one is that it is a Galois extension. Yes, so it is a Galois extension with a cyclic Galois group. Well, unlike this one, when characteristic is 2. Yeah. But the question is, what are extensions with a cyclic group of order 3. So can you say how to construct such extensions? Yeah. Yeah, so yes, you're right. So yeah, so you mean that there are Kummer extensions? Yeah, Kummer if K contains cubic root of unity. But what about so what is what if K is something, if K is a small field, yeah, like rational numbers, so what could you do? So in principle, of course, any extension of degree 3 is obtained by adding some root of cubic polynomial, yeah. So it's you can think of this as q of x modulo x cube plus ax plus b, yeah. So this is irreducible, but the question is, can you describe those polynomials whose Galois group is cyclic of order 3? Yeah, can you? So, by the way, what are the options for cubic for the Galois groups of the cubic polynomials? Yeah, so for Galois groups, yeah, so they can be yes, of course, symmetric group, and what else? Actually, not that many options. Yeah, either the whole symmetric group or the alternating group. So alternating group means that it is cyclic. So that's it. So we just have to
How do we use the second diagram? It's
A.
it's A. So it's A3 like a group of permutations.
Yes.
Even.
Even permutations, yeah. So how do you distinguish this case? Well, just so this. Do you remember how to distinguish?
The discriminant has to have square root.
Yeah, that's right. Yeah. So this.
Тут вот поступил отвод предложений из речь по третьей степени из числа.
Какого?
Непонятно какого.
Yeah. Maybe he thinks of Kummer extensions. But for Kummer extensions, we need to have the cubic root of 1 of unity. Yeah, so that's. Of course, this is the most general situation, but we will not assume that we have this cubic root of 1. Yeah. So so this means that discriminant is a square. Yes. Oh, that's right. So, but you see that the cubic root does not work in the case of real numbers, rational numbers. Okay. So, well, we can. So now we can try to solve the. So do you know what is the discriminant of this polynomial? By the way, what is the discriminant? So let me write this. Actually, this is minus, if I'm not mistaken, it's minus 4a cube minus 27b square. Yeah. So you can check this. This should vanish when polynomial has multiple roots. Yeah. So for instance, it should vanish when well, let's believe this, but but what do we want? We want that this is a square. So can you solve this? Can you find all rational solutions of this? So you see, we have three variables and only one equation. But of course, you can say that there are some equivalences, yeah, because you can transform this polynomial. For instance, if you divide what x by lambda, then you get the following. Oh, maybe multiply by lambda x cube plus lambda square a, lambda x plus lambda cube b. Sorry?
Okay, sorry.
We just multiply by lambda cube. So you see that this means that any pair A and B can be considered as equivalent to lambda square A lambda cube B. So for all invertible lambda. Okay, so yeah, so the question is, can you solve this equation? Yeah. So the point is that we need. You see, we don't have any square roots or cubic roots, so we have to find all solutions. But well, you can, of course, you can try to minimize the number of variables. For instance, you can divide everything by what? By c square. So this will be a over c cube times c plus 27 b over c square is equal, plus 1 is 0. So you see that you can express c in terms of these two ratios. You can denote this by alpha, and this is by beta, yeah, so then c will be, what will be? C will be minus 1 over 4 alpha cube 27b square plus 1. And you can, so this is c, and then you can write down what is a. A is simply alpha times c, that is minus 1 over 4 alpha square, 27b square plus 1. And b is, what is b?
It's beta times c, so it's beta minus beta over 4 alpha cube.
Yeah, 27 plus 1. Yeah. And you see that actually using this equivalence, so actually we're interested in A and B, so we got this A and B, and actually we can forget this alpha square, yeah, because we can multiply by alpha square here and beta square, beta cube here, or so you can think that A is simply, well, for instance, minus 27 beta square plus 1, and B is, what is B? B is,
it's, well, take lambda equal to alpha, and
twice alpha, minus.
minus 1/4 of A is minus 1/4 of the brackets, and B is minus 1/4 of beta, because we're forgetting about all right. So
Yeah, but you see, for instance, you can take twice alpha or minus to alpha. Yeah, actually, it doesn't really matter. Just well. So you see that. Yeah, it seems that that's it. The only thing we have to check. Yeah. So the only thing we have to check that this polynomial is irreducible. But well, I don't know how to do this. Yeah, maybe. But anyway, anyway. It is Well, it is definitely true for at least sometimes, yeah, so you can. Well, so at least we have some examples, yeah, so we have but
What just happened with when we turned when we used the Galois, a turned into minus 27 delta squared plus 1, and b turned into what? I'm not sure I can see it correctly.
no, you see that we have constructed certain pairs of A and B, and the only.
What happened with b when we used that equivalence? I just
You see, when lambda is minus to alpha, then we have to multiply this by its cube. Yeah, so it will be minus 8 alpha cube.
okay. Then there should be 27 and 7.
Thank you. Thank you. Yeah. So at least you see that we have at least one parameter family. Well, not at least, but at most, because we are not sure that these polynomials are irreducible. But if they are irreducible, then of course, and the Galois group is cyclic. And actually, we don't really use the assumption that our field is the field of rational numbers. So here, so what did we use? More or less nothing, but the only problem is that we don't know whether the resultant fields are non-isomorphic for different values of beta. Yeah, so that's the question. But maybe we should look at some. Yeah, maybe we should look at some examples like coming back to quadratic extensions. Yeah, because just to see, you see that of course you can say that A here actually is not so here in the case of Kummer extension, we can think of A not as an element of K properly, but of the quotient of the multiplicative group of K modulo the squares. And actually you can try to figure out how many quadratic extensions do some fields have. For instance, what are quadratic extensions of? You can, for instance, you can. I don't suggest to look at complex numbers, yeah, because there are. Well, it's not interesting. But for instance, you can try to look at real numbers, yeah. So when, of course, this is not very interesting, but still. So what happens if our field K is the field of real numbers? So what is the quotient of the multiplicative group by the subgroup of squares? Well, I would say strictly positive, because we are talking about the multiplicative group, yeah? Yeah.
The quotient should be z by 2z?
Yeah, it's just sign, yeah, so it's plus minus 1, yeah? Yeah, so, the quotient is just the sign, so plus and minus 1. And of course, there is only one non-trivial extension, yeah, corresponding to adding square root of minus 1. But you can also ask what happens if K is the field of say periodic numbers. So how many examples could you have here? So then k square over k.
So we take A from invertibles of K modulo squares.
Yes, because when you multiply by a square, it doesn't. Well, then your square root is multiplied by some element of k. It doesn't change the extension.
Understandable.
Yeah, so that's the question. How does the group of invertible periodic numbers look like? What is? How could you think of this group?
We can look at just целое количество чисел как обратный предел, может, с этим можно что-то сделать.
Yes, so yeah, you mean that you want to reduce the whole group to the group of integers, yeah, or invertible integers, yeah, invertible integral periodic numbers. Yeah, actually, yes. So what you say, you probably mean that you can present any non-zero periodic number as a product of power of p and some invertible periodic integer, yeah. Так, сейчас, Ира, вы знаете вообще о чем? Определение.
Можете напомнить целый логический.
So, integer, yeah, so periodic, yeah, maybe, yeah, so, so periodic integers, yeah, so periodic integers can be defined as, well, formally as a limit of rings of residues modular powers powers of p, yeah, so p is a prime. So what does this mean? This means that it is a compatible systems of residues modulo all powers of p. Yes, so compatible. I'll explain this. Compatible systems. So alpha n, where alpha n is a residue modulo p to the n, and compatible means that a n plus 1, you can consider a n plus 1, which is residue modulo p to the n plus 1. You can consider it modulo p to the n, and compatible means that it is alpha n. So when you reduce the next residue modulo higher power of p, then you get the previous one. So for instance, an example, well, so you see that, well, so for instance, we consider z mod 1 z mod p, 1 plus p modulo, which is modulo p square, 1 plus p square, which is a residue modulo p cube, and so on. And they are compatible in the sense that that when you reduce, so for instance, if you reduce this modulo p square, you get this one. When you reduce this modulo p, you get this one.
And this is an inverted limit.
Yeah, it's inverse limit. Inverse limit means that it is the collection of it is the set of compatible collections. Compatible in this sense, that each so you have maps between these rings or groups. So this just reduction modular lower powers of P, and compatible in the sense that these elements are sent to each other. Well, and of course you have a natural inclusion here, namely you can embed integers, because each integer has a residue in each of these.
So this is called integer.
Periodic, yeah, these are periodic integers. You can think of them as, well, you can present them as, you see, when you, for instance, when you use the decimal system, you can write integers, at least positive integers, using digits, yeah, from 0 to 9, yeah, so you can write 0, 1, 4, 6, and so on. And here you can also think of periodic numbers as certain numbers written in also using digits. So digits actually there are many ways to choose digits, and one of them, it's not the most natural. Not the most natural choice. You can choose digits from 1 to p minus 1. Yeah, so for instance, you can use this digits. It's not the natural one, but it's one of many possible ones. So, and then when you choose a collection of digits, of course there should be p digits, and then you write so any periodic integer can be written uniquely as A0, A1, A2, and so on, and so AI are digits. So.
And after writing first AO, then A1, and then A2.
Yeah. Yeah. Infinite, yeah, it is an infinite sequence of digits. Yeah. So the question is, maybe you see the difference with integers, namely we don't have here sign. Yeah.
But what does it mean in terms of those numbers?
Yeah, that's a good question. That's a good question. So let us call this A. So you have to define alpha, well, alpha, yeah, alpha. What is alpha n? Alpha n is a n minus 1 and so on, a naught, a1, a naught, modulo p to the n. P to the n plus 1, maybe. Plus 1, yeah. You see that, you see, this is an integer.
So it's sum of AO, then A0 plus A1B.
Yes, that's right, yeah, that's right, yeah. So actually, you can think of this as a sum from 0 to infinity, AI to p times I, p to the I, yeah. But the point is that this sum is infinite. Or this, yeah. So the question is, can you see the negative integers here? For instance, do you see -1? What is -1?
It's p minus 1 and zeros before after it.
So -1 is what?
It's
It's where a0 is pi minus 1
P minus 1?
and all the other digits are zeros.
no,
Oh no. They are
it has to be p
pi and
first -1, so it has to be
then pi square minus 1.
We don't have pi square, p square. We don't have p square. Our digits are from 0 to p minus 1.
Then it must be something. Yeah, it's
it's maximal digit on every step.
You mean p minus 1?
p minus 1 each step.
Ну, вроде да.
Ладно, смотри, сколько времени изменить? Сейчас p минус 1.
You see, so modulo p, it is -1, so it is p minus
So
1.
then the previous must be pi minus 1 modulo p square. Then, for example, pi minus 1 works actually.
P minus 1, yeah?
Minus 1. P minus 1.
Okay.
And
And
so on.
this is modulo p, this is modulo p square, this is modulo p cube. Yeah, you can think of this sum, yeah? So this,
Yeah, but which modulo?
you see that, look at this sum. So it is, it looks infinite, but actually we deal we work with residues modulo sufficiently high degree of p. Yeah, so actually you just truncate this sum somewhere. Yeah, so the point is that this sum should be -1 modulo high power of p. But actually, maybe I should ask you: do you know what is the sum of geometric progression? So,
It's 1 over 1 minus q.
for instance, this one. What is this? 1 plus. Well, I would say 1 over 1 minus p. Yeah. Yeah, of course, infinite, yeah. So, and what happens if you multiply this by, so what is this? How do you write this number? You write it just, so you see this 1, 1, 1, 1, and so on, yeah? So, and so you write that this is 1 over 1 minus p. And what happens if you multiply this by p minus 1? Yeah, you just guessed the sequence of p minus 1s, yeah? And this is -1, yeah? So that's how it works. Yeah, so you see the
This actually works with pi minus 1s.
Yeah.
Because it's in the first step it's pi minus 1, and then on the second it's pi minus 1 times 1 plus pi and so on.
Yeah, so it's well, actually, what can you say here? You can say that the finite sum is 1 minus p to the n over 1 minus p, and this is something very small, yeah, because it becomes 0 modulo sufficient when n is sufficiently big, then this becomes 0 modulo somehow. So it is
Well, it's for pi of absolute. Короче, по-моему, меньше конденсат.
yes, p is yes. So there is another definition. Yes. So maybe I should we should finish. Maybe I should say a couple of words about rational numbers, rational periodic numbers in terms of digits, and then. Well, maybe I should say what is the natural choice of what would be a more natural choice of digits. But maybe you know, do you know what is the most natural choice of digits? No?
In what sense?
Well, in some sense, because you see, actually, as digits, we can say we can take any collection of numbers. The only condition is that they should be they should present all residues modulo p. So actually you can modify these digits by adding any multiple of p. But the most natural choice is so natural choice is to ask that digits are roots of unity or 0. Yeah. So a to the p is equals to a. By the way, do you know why do they exist? No.
Is it really clear what you want to,
Hmm?
which numbers what you want to put, which numbers what you want to take?
Periodic.
No, в смысле, вместо этих цифр какие вы хотите взять?
As these digits, we want to take certain periodic integers.
В смысле, вы хотите записывать биологические числа вот этими цифрами?
Yeah. You see that it's not important in this presentation that these digits are from this particular set. Yeah. So the only thing we care is that the digits present all residue class modulo p.
Also, you can take the residues modulo p, and we can sort of in the order that they начиная с рождения, как multiplicative группы, или как?
Yes, but what you're talking is that there is a solution. There are solutions modulo p, but we want a periodic integer. You see? Yes. Why not? Why not? Well, maybe it's not very important at this point, but well, just this is just to remind you that probably last time, last time we have discussed Hensel's lemma, and Hensel's lemma told us that you can lift. So when you talk about solutions modulo p, this you should consider this as a first approximation to our solution of this. And then the Hensel's lemma says that if you have a first approximation and the situation is not very bad, then you can extend this first approximation uniquely to a full to certain root of your polynomial. Yeah, so in our case, of course, we have here we have solution 0. Yeah, so we can think of the equation x to the p minus 1 is 0. Yeah, and so derivative here is p minus 1 times x to the p minus 1. So that's yeah, thank you. Что?
Опять голос с другой стороны экрана
Да.
говорит, что нужно взять, берем левую гензеля, производная минус единица, значит все решения поднимаются, цитата.
Ну, я бы не сказал, что буквально. Yeah, so that's so the derivative is not well. Yeah, you mean modulo? Yeah, modulo p. It is invertible. Yeah, so this is p of x, and this is prime of x. Yeah, so Hensel's lemma. So for any a z mod p, there exists a unique solution, root of unity. Yeah, root of unity congruent. So p minus first root of unity which is congruent to a modulo p. So root of unity in which is periodic integer. Okay, yeah. So,
There exists a unique p minus first
root of unity, yeah, which is congruent to. I'm sorry. This a should not be 0. Yeah. Okay. Yeah. And so that's. But it actually doesn't matter so far. We don't really use these digits. But sometimes it is. It's more. Maybe sometimes it makes the picture more. Usual to, well, maybe easy to relate this to usual integers. Yeah. So the only difference is that we are not restricted. The length maybe of this can be infinite, but of course you can. We have addition, multiplication, because we have addition, multiplications on all residues. So, and also we have.
So can you please explain again how you want to replace those like not natural digits by these ones?
Just put here.
Yeah, I mean, but why is it works? Is it work?
What does it work? But what's the problem?
I mean, how does this work?
You just reduce. You see that.
So maybe let's think of it as a cross product of two vectors. So the first vector is our alpha that contains some digits, and it's an infinite vector. And the second is the vector that contains the powers of p. So the first coordinate is 1. Is the 0th power. So let's name this vector as beta. So that beta f is.
You see that actually take instead of these digits, take any. I mean, don't care about this particular existence of roots of unity. Just take any. So you take some digit which is Yes, you take any collection of p integers modulo p-adic integers. So the first one is divisible by p, the second one is congruent to 1 modulo p, and so on. Yeah. So, but p elements.
So the close example is equal to 1 modulo p. So this is, with this number we can replace 1, right?
Yeah. So if you want this in terms of this this is 1, 1, 1, 1.
Is it 1?
Yes, the whole, you see the numbers are compatible systems, yeah, so,
It is just 1 p numbers. In by this
yes.
number we can replace 1 in this case.
No, but one, when I say 1, here I mean 1, really 1. 1 means 1, 0, 0, 0, 0. And here, when I say this, I mean p minus 1, 0, 0, 0. But yes, but you can replace these numbers by, so you keep the last digit, and the rest you can change arbitrarily.
So as you said, this number can be 1 in new system of digits.
Yes, yes. You mean this? You can take as
Yes, this like the whole set of it.
yes. You mean you can take
Yes.
as 1. In principle, yes, yes. You see, the point is that you want to present any element in this form. So how do you do this? You reduce it. You reduce it modulo p, and look at. So you get some residue, and
So when you reduce modulo p, I got like the first, I'll get the first digits. When
yes.
I reduce it like p squared, it's the second one.
Yes. Then you after you reduced it modulo p, you get the last digit. Then you subtract the last digit and divide by p.
Yes. Okay. Yes.
Okay. Yeah. Now what is about QP? So QP. So in terms of digits. In terms of digits, these are. So do you know what are the rational numbers? Rational numbers are more complicated actually than p-adic rational numbers, because if you try to write rational numbers, then there are several options. You know that rational numbers may have infinitely many. For instance, what is 1/3? 1/3 is 0, 3, 3, and so on. Yeah.
P is a fraction field of ZP, right?
Yes.
So you can just write the squares of numbers
Like
like.
you mean as fractions? You mean as fractions?
Yes.
Yes, you can. But I mean in terms of digits.
You said that the invertibles of QP are just p to some power multiplied by ZP. Why is that?
Yeah, but so far we didn't have a definition of QP, so that's the problem.
Fraction field?
Okay, as a fraction field. Okay, but then you can, you know that any integer, any p-adic integer can be presented. Well, maybe not 0. There is a unique integer, positive integer, non-negative integer m, such that p to the minus m alpha is a p-adic invertible periodic integer. Yeah.
Oh, when this fraction field we can divide the invertibles and restate the invertibles.
Yes. So then we in the fraction field we just so this is an invertible element in integers, and then we're only left with some power of p, which may be negative. But let me write what is qp in terms of digits. So in terms of digits, these are just some sequences of digits, a2, a1, a0, and then we place comma, then a minus 1, a minus 2, and so on. But you see that here we have infinite sequence of digits after the comma. But in the case of periodic numbers, we have only finitely many. So you see the difference. But, well, you can say that here we have finitely many digits before comma. So in a sense, this situation is symmetric. Yeah, so we have only finitely many digits after the comma. But so what does this mean? This means that so what is so if we write this denote this by alpha, this means that that there is some power of p, namely here p to the n, such that this element is irrational. Yeah, so it is integral. So this will be a2, a1, a0 without comma. Yeah, minus 1 and so on. A minus n. So it is an integer. Okay. All right, and so yeah, so the claim is that this is a field. So this is a field, and well, you know how to add to. Do you know how to add numbers and how to multiply them?
In digits, I think we just add them like the normal way.
Yes.
With the topic.
Yes, exactly. Yeah. So you start with the last digit and continue to the left. Yeah. Okay. Yeah, but actually, as Masha said, you can just think of periodic numbers as the union of well, as a fraction field. But this simply means that you consider you see that any periodic number becomes integral after multiplying by a certain power of p. So you can think of periodic numbers as the union of integral periodic numbers divided by certain powers of p. Or, well, of course, there is another definition. Another definition is that another definition of QP is just its completion. And this is the completion of the rational numbers with respect to the following periodic norm. It is defined as follows. So the norm of A is p to the minus n, where A p to the p to the minus n, A is is well, P. So maybe I should write C over D, where C and D are integers and that are not divisible by P. Yeah. Okay. So just you. So you. This means that you say that two numbers are close to each other if their difference is divisible by high power of P, and divisible in the sense that when you divide.
With respect to which operation?
With respect to this this norm or distance, yeah, maybe I should, if you don't like norm.
It's a topological completion.
Hmm?
It's a topological completion.
Yes, in the usual senses, you know this fundamental sequences. Yeah, so with respect to the distance, to the following distance, d of x and y is equal to x minus y p, and this norm is defined as follows. Well, here it's not important. So far, it's not important that this is p to the minus n, because here, I mean,
where p, well, maybe the norm of the number is where p to the nth a is in zp or what? Нет, значит, получается.
you see,
So the question is, why do you say that this element is an element of some? So C over D, what is it?
C, you see, what is
it equals
what is
C over
oh
D.
yeah, thank you, yeah. Yeah.
Right then. And then we say that C and D are residues of.
No, they're not residues, they're integers,
They're integers.
not divisible, both non-divisible by p, yeah. Yeah, so yeah. So now we want what do we want? Yeah, we want to yeah, maybe I hope that now it should be clear, this equality, that what is QP, this one. Yeah, so maybe I should erase this one. Okay. Yeah. So so now what is yeah, maybe we should discuss in more detail how does multiplicative group of the periodic numbers look like. Yeah. So first of all, is it clear that any non-zero periodic number is a product of a power of p and an invertible integer? Well, actually, this simply means
What are actually these invertible integers? So what do they look like?
Invertible.
So non-zero in every digit.
Wait.
So every digit is non-zero.
No. You mean non-invertible?
No.
Non-zero?
Invertible
Integer.
So are they just
A naught is not zero.
so they all are non-zero?
No, only A naught.
Only a naught is non-zero.
No, yes.
It doesn't follow from A naught not being zero that all the others are non-zero also.
No. You see, there is one.
It can be
One.
pi modulo pi square, for example.
Да, красиво.
you see that if it is invertible modulo p, then it is invertible modulo p square, and so on. Okay.
Так, тут было предложение, можно сказать, что ZP со звездочкой это просто степенной чик. Это 1 плюс P умножить на ZP и взять степенной ряд.
Это который нет.
Взять этот логарифм как формальный степенной ряд. И вот. И сейчас вот последовало, что похоже это неправда.
Для двоих это неправда.
Ну как, если у нас invertibles это что первое не ноль, то если число не ноль, то в какой-то момент там цифра не ноль. Вот ее мы возьмем, и вот на эту степень мы проверим.
Yes, Masha explains this equality. Yeah, so she says that if so we have so here is our alpha, and we assume that alpha is not zero. Yeah, so if alpha is not zero, then there is at least one non-zero digit, and we take the first one, for instance this one. So suppose that alpha minus n, a minus n is not zero. Then we multiply alpha by p to the n, and we get an integer.
So say that alpha minus n is not zero?
Yeah, so if our element is non-zero, then it has at least one non-zero digit.
And if n is, it's for example a2.
Yes, if then yes, if this is a2, then well maybe you can change the sign if you wish. Of course, it may be a2, so the first non-zero digit. Then we put here p to the minus 2, and we get an invertible integer. So because the last digit is invertible, is non-zero. Well, we should say. We should say invertible. Yeah, maybe I was a little bit sloppy when discussing digits. No, it's okay. It's okay. It's okay. Yeah.
At some point in the cumulative limit.
Yes. Mm-hmm. Yeah. Okay. So that's our decomposition here, and now we want to discuss the structure of invertible integers. So as Vladislav suggests, we may look at. So first of all, we have to come back to our digits of this type, which are roots of unity. So we know that roots of unity are embedded here. So z mod p can be embedded. This is a group embedding. So roots of unity. Roots of unity. Да, но только, but only of degree p minus 1, so because those of them, so maybe I should write this p minus first. You see, it's a non-trivial embedding because it's a non-trivial embedding because its construction uses Hansel's lemma. Namely, to each residue here, we can associate certain root of unity, but in a sense it is rather implicit. Or, well, of course you can try to write it more or less explicitly, namely, well, you can take here A and well, you have to solve equation A plus TP to the P minus 1 is 1, yeah, so it's well, so it is possible to write a certain sequence which converges to this root, but maybe it's not very explicit. Okay, yeah. So, and on the other hand, there is another. There is a complementary subgroup, namely those elements here that are congruent to 1 modulo P. So you can. So the conclusion is that CP is isomorphic to residues modulo P, invertible residues modulo P, times 1 plus P ZP. So now you may ask how this group, so this is a group under multiplication, and you may ask how this group look like. So in principle, so as again as Vladislav suggested, we can take a logarithm. So do you know what is a logarithm? Logarithm. What is logarithm? Yeah. So the logarithm 1 minus x. Let me write this way. It is x plus x squared over 2 plus x cubed over 3 and so on. So we have to check that this series converges. And try to, well, in principle, so if we want to relate these two, so this is multiplicative group, and this is additive group, and so ideally we would like to have an isomorphism. So how to construct, how to check that this is an isomorphism? If you have a map from one direction, you would probably want to construct a map in the opposite direction. So yeah, so yeah, the exponential, so what is, you know that exponential in our case is much worse than logarithm, because do you know what is the exponential? You know that it is a quite terrible thing, namely you divide by factorials. And this is not really good, yeah, because factorials have denominators. Well, even logarithm has denominators. So, but so coming back to the logarithm. What can you say about its convergence? Its convergence and its
We have to check the relation. But the relation of an integer, it gets smaller if we forget to say this.
yeah, so you see that actually here we deal. So what can you say about x here? X is not an arbitrary. Well, it's not completely arbitrary. It is divisible by p, and that's already good because so if p say w, yeah, to the n over n. So what can you say about this? So what is the, so we just assume that w is an integer, and we want to know whether this is an integer and whether this tends to 0, yeah, when n grows. Oh, by the way, I should say that this distance. So you know that when you want to check that something is a distance, the only thing you have to check is the triangle inequality. Yeah. And what is good about this triangle, this distance, is that in here all. Yes, it is not Archimedean, and so all the triangles are equilateral. As a, how is it called? As a Isosceles, yeah? Yeah, so, yeah, so, yeah. So they are bigger, yeah, bigger or smaller? Bigger sides should be equal, yeah? Ага. Хорошо. Yeah, thank you. So yeah, so the point is that, yeah, so that here p appears in degree n. Yeah, so here is, so this is like p to the n. And here p appears in degree, well, we don't know in which degree p appears in n, because maybe it's not divisible by p at all. But anyway, the maximal possible degree of p that appears in n is logarithm of n, well, maybe integral part of the logarithm of n with the base p, yeah, and of course this tends to 0, yeah. So it's so this is well, maybe I should write that less. I don't know how to write this. Not proportional, because you see that actually, well, maybe I can write this way, that periodic norm. So yeah. So why did I say that this distance is very special? Because unlike real situation, for the convergence of any series, it's sufficient that the general term tends to 0. Yeah, if that's the funny property of non-Archimedean distance, is that if the general term of the series tends to 0, then the series converges. Yeah? So, and this is just because of. Yeah. Now, yeah. Maybe I should say that what is, yeah. So this is less, yeah. So this is less than or equal to. Yeah. So and this is p to the minus n minus logarithm, and you see that this tends to 0. Okay, so this converges, but actually what we want is that in fact this is a map not just to the p, but to if you look at this degree, then you will see that it is strictly positive. So it will be a map to p times zp. Well, yn minus logarithm p to the n is strictly positive, yeah? This one. That's it. That's what I'm saying.
And we can just look specifically at the norm of this thing, and then the logarithm just becomes n.
Yeah. So you want to take p power, yeah?
And where I can
Yeah. Yeah. You're right. You're right. Yes, you're right, because this gives us minimal possible n, yeah, with the same power of p dividing it, yeah. So actually, yeah. So we can so sufficiently sufficient. It is sufficient to look at p to the n over p to the m, yeah, something like this. Yeah, because we want to have maximal power of p in the denominator, yeah, and the minimal degree in the numerator, yeah. So how do we do this? We get to get maximal, we just take power of p here instead of n. And here, this gives us minimal possible power of p in numerator, so it will be p to the m minus m. Yeah, and so the point is that this is always positive. Yeah, is that true?
I can like I can write what I was from in more like detail.
No, I think, well, you just check this at 0 and take derivative and to make sure that this grows. When you take derivative, you get what is the derivative with respect to m? It will be logarithm of p times p to the m minus 1. And of course, this is positive. Yeah, even so this grows, yeah, and even at 0, it is even at 0, this is logarithm of p minus 1. So it is wait. There is, you see that there is some subtlety. It appears here. It is not positive if p is 2. Because what is this? This is logarithm of p over e. Yeah, so that's the subtlety. And there is a reason for that. Do you know which one? Because so the point is that it is not. It is an isomorphism only if but anyway, yeah. If p.
Wait. I still have a question.
Yeah.
So what I would do, I would just like write the norm as pi to the p to the minus n minus something that is evaluation of w to the n, and just plus evaluation of n, just normal evaluation of n, which is less or equal than logarithm of n. Oh, that's where it's the problem break. Where evaluation, like how much p there is in n that's less or equal to logarithm. Does that equal to break when p is 2?
Yeah, actually, you're right that there is no problem. Well, there is another problem when p is equals to 2, but you're right in the sense that it will be. You see, the problem is that we cannot conclude immediately that it's not true that the function grows. You see that the function is something like this. So here is 0, here is 0, 1. That's the problem. When p is equal to 2. But there is no contradiction because in fact the value is at 1 is also positive. You see, when p is when m is 1, then we get p minus 1, which is also positive. So there is no problem here. We want to prove that its value, this logarithm take values in multiple.
Там еще просьба повторять вопросы из одной из аудиторий, потому что не очень хорошо слышно.
Yeah, so the question was what we are doing, yeah? Yeah, so we are trying to prove that the image of the logarithm is in periodic integers divisible by p. That's what we're trying to show. Yeah, so and yes, and this means that we want to show that all these terms are divisible by p. Or in other words, that this difference or this difference are strictly positive. Maybe even this one, yeah? Yeah.
Can I just write the periodic norm of this thing, the relation of that?
Yes.
Just write in the...
Yeah, okay.
Okay. Thank you. I think I broke something. Согласна. Damn. Okay, I'll just hold it. Okay, so we have this. The periodic norm of our summand, which is p to the minus, I'll just take the n from here, and 1 plus yes. This is just the periodic relation of this. So this is p to the nth, and then p to the whatever degree that is inside here. That's that.
And this lower
It's the maximal degree of p
contained here.
Can I sorry. So, and then plus whatever is here. So I'm dividing. The summand is divided by n. So here this is the negative order of the negative this of this. Sorry. So then I can just say that this thing, this order, is less or equal than just logarithm. The logarithm, the pth logarithm of n. So then I just say that this is less or equal than p to the minus n times p to the minus n by whatever this is, and then times just p to the logarithm of n, which is just 10. So less or equal than that. So which is this is just less or equal than n divided by p to the nth. It's just I'm saying that this is 1 or less, because we were saying that x is pi w because x is divisible by pw because x is divisible by p. So then the valuation, the p valuation of this, of the w, is not smaller than 0. Then this is smaller than 1. No, not bigger than 1.
What is not smaller than 0 and why?
Yeah.
Sorry.
No, yes, actually, you just. Yeah, so actually you can just forget this because well, in this you can forget this in this equality, but you can forget this in. Yeah. So. Yeah. So you just you omit this when you pass to this estimate. Yeah, because it is always non-negative. Because w is an integer, so it's it means that yeah. So w is an integer, so it is it's this order is always non-negative. Yeah. Well, by yeah. So we consider only those. You see that our x is something divisible by p. And this means that w is integer. So it's yeah, and then you just yeah. So as Masha told us, so it is n over p to the n, and this is actually that was the same the same question. So, and the claim is that it is always, it is strictly less than 1. Strictly less than 1 means that actually, you see,
It's just the sum of the n by n divided by p to the n. The sum of that converges. So and the difference between if the sum of the norms converges, then the original sum converges to.
yeah. So actually, we want. You see that there are two things. First of all, we want this to tend to 0 when n goes to infinity, and the second, for each n, we want this to be strictly less than 1. So the first one, we need the first condition that it turns to 0 needs. We need this to make sure that this series converges. And the second, that it is strictly less than 1, is needed to make sure that the image is in P, is divisible by P. Yeah, so, well, of course, this tends to 0. Is that clear? Yeah, it is, yeah. And it is less than 1. Well, it is also more or less clear because it is, we have to.
It can be 1 if n is 2. If n is
No. That's not, the problem is, you see, the problem is with the exponential. So far we have estimated, yeah, so I assume, may I ask, can we assume that we have shown that that logarithm is well defined and its image is here? It's target is here.
So, once again, this, we get that n over p to the nth is less than 1.
And tends to 0. And
yeah, okay. And then why is the tangent of logarithm in p p?
because each summand is strictly less than 1, and therefore the whole sum is less than 1. By the
So just because it's divisible by x, which is divisible by p.
yes, yes, you can think, yeah, you can say it this way, is that this each summand is less than 1 means that each summand is divisible by p. Yeah, so if each summand is divisible by p, then the whole sum is also divisible by p. Yes, and this means that each summand, that this summand is divisible by p. Yeah. Yeah, but now
Okay, then understandable.
we need this to show that first of all a logarithm is well defined here, and the second that it is a map to the integers divisible by p. We want in principle we want to relate these two groups. And moreover, the claim is that they are almost isomorphic, almost in the sense that they are isomorphic when p is greater than 2, and you will see. You will see. So you see that the point is that we want we try to construct the map, the exponential. Yeah. So we have to. So you know what is the exponential? Yeah, it is. Now we want to we play the same game, but with n factorial in denominator instead of n. Yeah, so pw n divided to the n divided by n factorial, and this is not that evident. Yeah, so this will be p to the n over. So what is this? This is you see that you have to find the maximal power of p, which divides n factorial. Yeah, so you take n over p, take the integral part, plus n over p square, and so on. And you can estimate this. You can estimate this by what? Sorry, maybe I should put here the norm. It will be a p to the n minus n over p minus 1. So this is p to the p over p minus 1 n minus. Yeah. Sorry, minus, yeah. So this, yeah. Okay, yeah. So what do we see? We see that is that correct? By the way, no, it's not. It's not correct. Yeah, it's not true. It's p minus 2. P minus 2. Yeah, and so you see that we get a problem when p is equals to 2. Yeah? Something wrong here. So, but the point is that we, yeah. So first of all, if p is greater than 2, So if p is greater than 2, then we get a well-defined. So this will be. You see, then general terms tends to 0. Does it? When n tends to infinity, so it is 0 is the limit. Yeah. Hmm. Okay. Окей. Ага, ну спасибо. Спасибо. Okay, yeah, so you see that we don't, I mean, it is quite essential. So here we just have an estimate, but it's sufficient for our purpose. So yeah, so the conclusion is that then this is an isomorphism. So then 1 plus p zp is isomorphisms. So these are isomorphisms of p zp. Yeah.
So you have shown that it converges?
Yeah, so first of all, it converges, and you see that this is always strictly less than 1. So this is strictly less than 1. If p is
So how do you get that? Maybe it's so one. It's isomorphic to zp or
pzp. So you see that this is logarithm and this is exponential. And they are, you see that you can check formally that they are mutually converse to each other, yeah? So it is a formal problem. The only non-formal problem to make sure that they converge and that they are, yeah, so that's the problem. And
isn't our so aren't the invertibles of 1 plus p zp isomorphic to zp?
well, of course you can divide by p if you wish here, but if you just take logarithm, you get integers divisible by p. By the way, maybe you have, I'm not sure if you, I think it's first year program in algebra. Do you know what is the structure of residues modulo p to the n? How this group look like? How does this group look like?
E to the n minus 1 by p minus 1, something like that.
Yeah. So but the point is that to construct this isomorphism, you actually do play the same game. Yeah. So you play the same. You use these isomorphisms, but reduce them modulo p to the n. Because to construct, so what probably Masha says, so that this is, well, of course this is p is greater than 2. Z mod p to the n minus 1. So how do you get this? You just use, actually, you use this decomposition, then a logarithm, and reduce these isomorphisms, reduce modulo p to the n, and that's how you get this. Because, but of course you can write this on the level of. You see that in principle you can write this logarithm on the level of residues modulo p to the n. Yeah, but but it's I would hesitate to divide by big powers of p.
Он говорит, что у нас просто циклическая будет группа, если у нас p нечетная, и если p двойка, то это z под 2 на z по 2.
Да-да-да, но как построить изоморфизм? В этом вопрос. Как бы абстрактно. Нет, абстрактно, да, абстрактно. Yeah, abstractly, yes. You're right that in the sense that if you know the order of this group, well, you can use certain arguments to show that this is a cyclic group, but to construct this isomorphism, you need logarithm. I mean, there are no natural ways to do this, I think.
So can you just repeat how do we use logarithm to construct this isomorphism?
Yeah, so you see that what is this? This is just reduction of periodic invertibles modulo some power of p, yeah? And what do we do here? We first of all we say that there are roots of p minus first roots of unity here. So and then this gives us a splitting of this group into the product of pth roots of unity, which are identified. So you can identify pth roots of unity with the residues modulo, invertible residues modulo p. Yeah. And so this will be the first factor, and the second one will be those periodic integers that are congruent to 1 modulo p. And then you use this isomorphism. Okay. So yeah. So now about p equals to 2. P equals to 2. Yeah. So actually, what can we do in the case of so what is wrong here? So actually, we can try to check whether this is essential. Whether this, you see that these are just estimate. This is an estimate, but actually it's not just an estimate. I mean, it's a real problem because 2 to the n over 2n factorial. So let's try to estimate this. So what is this? This is 2 to the n minus. So what is this? This is, we have to divide this by 2. So maybe 2 to n minus 1 minus 2 n minus 2 and so on minus 1. Yeah. So this is 2. And what is written here? So here we actually get 1/2. Yeah. You see. So the conclusion is that this series diverges. Yeah. So it's not. So what do we do? We just, well, it diverges, but diverges because it doesn't tend to 0. So yeah, we just estimate each term. You see that the numerator is divisible by p to the n, and the denominator is divisible by p to the integral part of n over. You see that each pth number is divisible by p. And each, so there are n over p integral part of n and p such numbers. And each p squared number is divisible by p squared.
Okay, how do we estimate
The sum is it's a geometrical progression. So we say that it is we remove these integral parts. We just forget them. Yeah. So we get something bigger. So and we add more summands. Yeah. So it will be an infinite sum. Of course, this sum is finite, but we make it infinite. And so that's yeah. And so this sum, this infinite sum is n over p minus 1. This is just geometric progression. You see that's 1 over p over 1 minus 1 over p.
I feel like we lost the minus sign somewhere because
No. No. You see that this sum is bounded by this one, yeah? This sum is less than this one, yeah? Here? Because we just forget, if you don't want to forget w, then it will be equal. Hmm? Mhm. Это? You see that the geometric progression is 1 over p, yeah? So okay. Yeah, so so it doesn't work, but it's not a big problem because actually what can you do? You can you see that we assume that p is a prime, but actually we can assume that p is 4. Yeah. We just look at this. So we can consider. So what can we do? We can look at the following picture. So we consider. So maybe. So this is 1/2. We consider logarithm from something congruent to 1 modulo 4, and then it will be mapped to integers divisible by 4. And in the opposite direction, there will be an exponential, which maps again integers divisible by 4 to integers divisible congruent to 1 modulo 4. Yeah, and the claim is that these are mutually inverse isomorphisms. So these are isomorphisms, and so the conclusion is that when so this is so what was wrong with those that are just odd, that are congruent to 1 modulo 2? The problem was that actually logarithm had a kernel. So you see that the problem was that 1 minus 2. So what you see that 1 minus 2 is congruent to 1 modulo 2. Yeah. So do you know what is 1 minus 2? It's minus 1. Yeah. So and what is the logarithm? Logarithm of minus 1? No. You see that our logarithm is well defined. Our logarithm is well defined here. So it is a periodic number, more or less divisible by p, yeah, by 2. So the question is, what is logarithm? So it is well defined. So the question, what is this? What is logarithm of minus 1?
So it's sum of minus 1.
No.
Or 1
No, no. So what is logarithm of minus 1? Maybe I should write minus logarithm. Minus logarithm of minus 1. This is 2 plus 2 square over 2 plus 2 cube over 3 plus 2 fourths over 4. Well, of course you can try to look to calculate several first. For instance, you see that this is 2, then this is also 2, so you get 4. So this is, but here you also get 4. So this is also 4, so this will be 8. 8 plus 8 over 3 will be 32 over 3. 32 over 3. This, you see, 2, this is 2. This is also 2. 2 plus 2 is 4. And here is also 4. And 4 plus 4 is 8. And 8 over 3, this is 8 over 3 plus 8 is yeah, so the question is, what is logarithm of minus 1? Mm-hmm.
Ну, Влад утверждает, что логарифм минус единицы это 0, так как два логарифма минус единицы это логарифм от единицы равно нулю.
Yeah, совершенно верно, да. Yes, exactly. So the point is that twice logarithm.
Если это гомоморфизм.
Yeah, but it is, yes, so the point is that this is a homomorphism for formal reasons, because you can just take you can check this as a formal identity. Logarithm, yeah, so that's the point, that you know that it is a it is a homomorphism for instance for the reals, yeah. But if you know this for the reals, then you know that it is true formally. And if it is true formally, then of course it is true for whenever this is a convergent series. So the point is that logarithm twice logarithm of minus 1 is logarithm of minus 1 square, and you know what is minus 1 square, yeah? And therefore logarithm of minus 1 is 0, and therefore the conclusion is that invertible. So what can you say about this? Yeah. Of course, well, here we have nothing, yeah. So we have plus or minus 1, so plus minus 1, and when we then we can say that this is a product of plus or minus 1 and those integers that are congruent to 1 modulo 4. And those congruent to 1 modulo 4 are isomorphic to 4. So the logarithm identifies them with the z2. Well, you can say right this way. Is that correct, by the way? Yeah, I think so. Okay, so is that clear or not really? Или не очень? Okay. Then so what can we do with that? We can try to see what kind of extensions, well, cyclic extensions or abelian extensions of those periods. You see that we sometimes we can use Kummer theory, for instance, when we deal with quadratic extensions, because we always have, this in characteristic 0 we have square root of 1, yeah, so which is -1. And here, in the case of periodic field, we have also a p minus first roots of unity. So the question is, what are cyclic, cyclic, or maybe cyclic extension of QP of order of degree p minus 1, yeah, p minus 1. Cyclic degree, maybe degree p and 2, maybe, yeah. So what can you say? How?
Kummer extensions.
Yes, they are Kummer extensions, but can you describe them? I mean, no, to say how, at least to say how many these extensions are there.
Что понимаешь, что у нас типа cyclic extension?
Это нужно группу Galois изучить. Да, но здесь, вот как Маша справедливо заметила, это расширение Куммера. Поэтому, в смысле, что корни есть соответствующие степени. Yeah, so we do have corresponding roots of unity. So to get such an extension, you just have to add to Q certain root of an element. So you can, so actually we deal with extensions of the following type. So for instance, for the degree of p minus 1, you just have to add root of degree p minus 1 of certain element. The only condition is that it is not in the it's not a power of it's not a power of an element, so which is d, yeah, d divides p minus 1, yeah, and of course, yeah. Or in the case of degree 2, you just square root of a. But the question is, you see that it may happen that you take in different a's, you get the same field extension. So the question is, how many different cyclic extensions of QP can you get this way? Yeah? They can be the same. For instance, if you multiply a by b to the p minus 1, yeah, then yeah, you see that this will give you the same field extension.
So first roots of which numbers are linearly independent?
Yeah, or yes, or another way to say this is to ask what is the quotient of QP. Yeah. So you can say that actually you to get an extension you take not an element of the multiplicative group but an element of the quotient by the corresponding powers. Yeah. So well, in principle you have to look at subgroups. Yes. Actually, you are looking for subgroups of this group. Yeah. So cyclic subgroups. Subgroups of order p minus 1 in this quotient. So that's, or the same question with QP modulo squares, one instead of p minus first powers. Это фактор. Это, you see that you consider the multiplicative group of the field of periodic numbers, and consider its quotient by p minus first powers. Because you see that. Yeah, of course, yeah. So this will be the same element in the quotient. Yeah.
So the invertibles in QP are the powers of P by invertibles in ZP. So that's we can see it as Z, the group Z multiplied by ZP, where we take Z as the additive group. So then the P minus first powers of these are P minus 1 by Z, Z additive group, multiplied by P minus first powers of invertibles in ZP.
Yeah. So. So you mean that? So we look at this. So we have this simply cyclic group, yeah. So and we quotiented by index p minus 1 subgroup. This is from P. Next we have roots of unity, yeah. So this is again. Yeah, so roots of unity, yeah, so we maybe I should write here square, yeah, because, but now it's a different, maybe it's not a good idea, yeah, well, let me write this Z mod P star, these are roots of unity, and next, this one. It comes. This comes from powers of P. This is simply cyclic group modulo P minus 1, and the second comes from roots of unity. And what else, Masha? What did you say?
I don't know. I was just going to propose the quotient of invertibles in ZP by the P minus first powers of them, and I don't know.
Yeah, but may I ask you a question? So what is what you see that here we have raising to the p minus first power. What does how does this look like after taking logarithm?
Multiply it by?
Yes, it's multiplication by p minus 1. And how does So what is the co-kernel of the multiplication by p minus 1 on zp? Which elements of zp or p times zp are divisible by p minus 1? What is divisible by p minus 1?
Well, for example, b to the nth minus 1.
Okay, and
So, actually,
is that the only divisible element? Do you know how to divide by p minus 1?
It's difficult to work with periodic numbers.
You see that, well, let me explain you how to work with periodic numbers. You see that it is so you know how to work with geometric progressions.
Probably.
Yeah. So
Yeah, okay, this is minus 1 plus p squared plus.
you see that it is invertible. Multiplication p minus 1 is invertible.
Okay, so the kernel is nothing.
So everything is divisible by p minus 1.
Yes.
That's it.
one second, please.
You see, we just told that every periodic integer with non-zero last digit is invertible. So here, the last digit is p minus 1.
Where we want.
So the last digit is p minus 1, then it's invertible, then we can
Then-
just invert it and multiply by it.
Yes, you see that raising to the p minus first power here becomes multiplication by p minus 1, and therefore, but p minus 1 is invertible, and therefore everything here is divisible by.
Zero.
It is 0, yeah. So so the quotient is 0. So that's it. So that's the answer. So we have So we just have to describe cyclic extensions, or maybe not cyclic extensions, or maybe all abelian extensions of period p minus 1. We just have to look at subgroups here. So there are at least you see that there are only finitely many of them. Yeah. And what about squares?
We can do the same thing, but it's not going to be like the first quotient is going to be okay. First quotient is just z by t from the power of p, and then
Yeah. So
the second powers over the first powers of z by tz, and then if p is not 2, then it's again invertible, so the last one.
yeah, so just maybe I should just stress that here that p is greater than 2, because otherwise it's yeah, it's not interesting. So yeah, so you say that if P is Masha, when you say that so the first factor is z mod 2, and the second when you assume we assume that P is P is odd, yeah, and what will we get?
If P is odd, then the last part, which is the 1 plus P is a P by multiplication or just P violation. If we multiply that by 2, it doesn't change also because 2 is also invertible.
Yeah.
So what we get is only the z by 2 the beginning from parts of P, and then the second part, which is z by pz invertibles by z by pz invertibles squared, which is those are different depending on if P is congruent to 1 or 3 or 4, I think.
I don't think so, because no. So you mean that? Wait, you see? Yeah. So let me repeat, because it's not translated to somewhere. Transmitted. Yeah. So yeah. So you're right that this part is 2 divisible for P greater than 2, of course. But here you see that this is a cyclic group of order P minus 1. So it doesn't matter whether P is congruent to 1 or 4. So in any case, it is a group of order 2. So it is isomorphic. This only affects whether minus 1 is square or not.
Oh, right, sorry.
Yeah, so it's okay, and so this is for P equals greater than 2, and for so the question is what happens when P is equal to 2. So Q2 square. So what is this?
If P is equal to 2, I think that's previous.
So well, the first part is the same, yeah. So this P power, well, 2 power. This will be, of course, z mod 2z. Next, where is it? But
That's just z by 2 again?
z by and you mean plus minus 1, yeah? Yeah.
And then there's one part which is for the addition that turns into 80, for the 2 by addition, which turns into 80 2 by addition, and then that quotient is z by 2 again, I think.
Yes, so you just, you have to, where is it? Where is it? Yeah, it's here. Yeah, so we just consider the quotient of this group by its subgroup of index 2. Yeah, so it's again one more z mod 2. So it is a group of 8 elements. Yeah, so it's well, again, some not that many, but still. Okay. Well, so yeah, maybe we should
уже точно... Хотя уже 60 минут осталось, можно без перерыва.
Ну, я не знаю, если все устали, то можно прерываться.
Сделать на 10 минут. Ну, на 10-15. Или же просто уже сегодня...
Давайте, может...
В целом мы заканчиваем в 7:30, сейчас 6:55.
Ну,
Ага.
да, но это там с учетом получасового перерыва.
Мгм. Не, ну, давайте, может, тогда действительно что-то, по-моему, все утомились. Давайте мы как бы считаем, что мы окончили его, давайте лучше обсудим, да, что там, что тут неясного, да.
Кстати, вот вопрос.
Да, ну, да выключайте, наверное.
Подожди, давай сначала обсудим вопрос по поводу экзамена.
Да.
Потому что я вам написал, вы так и не ответили.
Я считал, что я ответил.
Вот. Ну, давайте тогда это обсудим просто.
Да, давайте.
Просто
Да.
зафиксировать, что
Yeah.
все...
Yeah, so, yeah, so the question is about the exam. So exam, I wrote that I proposed. I don't remember what did I. Alright.
On the just statement, so the deadline for the homework that you proposed was on the 21st, and then you give out the exam on the 21st, and then the deadline for that is on the 27th.
Yeah, something like this. Yeah. Yes. Yeah. So. Because the reason was that some people are abroad, so anyway it should be a take home.
I'm not complaining if you push the deadline for the exam and that's later. I'm not complaining even though I probably won't be able to do anything about it although like 28.
Well, I mean, it's for me it's not critical. I mean, if you really need more time, it's okay. But the only thing I don't know is the deadline for учебной части.
Разрешить ли учебную часть так сделать?
Я просто я не знаю, когда у них там у них какие сроки. Вот.
Учебную часть? Ну,
Да.
у нас вроде сессия до 31 включительно.
Скажем так, я не хочу 31-го.
Ну, не, я имею в виду, что...
Официально, да. До 27-го экзамен есть, так что до 27-го их точно можно.
Вот. Мне кажется, даже до 28-го, 29-го спокойно.
Ну, наверное, но когда отчет уже надо сейчас.
Еще вопрос, все-таки, как у нас будут оцениваться? То есть, получается...
Ну вот, значит, там я написал, что из 6 домашние, вот как бы то, что было вот висело там все это время, как бы из 6 баллов, и из 10 баллов экзамен.
Так, а как итоговая оценка будет ставиться? То есть, получается,
Ну, суммируется.
экзамен плюс...
Да.
Ага. Понял. То есть, получается... Сейчас на экзамене у нас будет какая-нибудь программа? Заранее вывешенная?
Будет заранее вывешенная.
Ну, просто билеты будут известны.
Билеты, нет, это будет, it's a take-home exam, there will be several problems.
Все, да, точно.
But if you want...
А насколько... во-первых, будет ли сейчас? То есть задачи, они как? Будут как те, которые были по Малфае?
Да, вопрос, задача скорее теоретически или скорее посчитать обычно игру была там
Да, yeah, so the problems like calculate some Galois group. Что, не, что, нельзя? Техническое.
Ну, просто да, это даже обидно, что я что теоретически из 6, а технически из 10.
Да, ну просто мы, скажем так, в основном именно техническую часть почти не делаем. Вот, то есть мы в основном что-то...
По технической части, вот лично у меня, например, будет большая фора, потому что у меня я на втором курсе, у нас вот сейчас только что была теория была, я сегодня контроль написала.
По технической части я подразумеваю именно непосредственно подсчеты в конкретных случаях. Здесь мы просто разбираем
В смысле, вы за всех остальных переживаете?
Я это сказал.
Ну,
Это же у меня это выше, значит, что у меня это что даст, что я тоже написала, простите. Но все равно, как бы, не знаю, просто если так, то, наверное, ну просто обидно, если вот эти вот подсчеты, которые мы не очень-то и делали, и вообще, если я говорю 10, а вся теоретическая часть из 6.
нет, так это же, по-моему, все. Не, ну, смотрите, а собственно какие варианты? В смысле, что... Нет, понимаете, это же it is a take-home exam, so...
So we have a week to calculate this and that.
Yeah, and on the other hand, I cannot ask to prove a theorem because everything is written somewhere. Yeah. So. Well, of course, we can try to split this. I mean, to make for some people make it take home, for some make it oral, for instance. But I'm not sure this will be. Actually, I don't even know the list of those who subscribe.
The list of people who are officially go here, and the list of people who actually go,
Yeah.
I think it's very different from what I got.
Yeah.
And also, should we write in English or we can choose
English.
Russian?
В смысле, если вы, то есть вы хотите сказать, что у вас русский не родной? Нет, если вам очень сложно, если вам сложно писать по-русски, то, пожалуйста, пишите на каком-нибудь другом языке.
Хорошо, осталось вспомнить немецкий.
Да.
Хорошо.
Так, и еще что-то хотел спросить. Получается, у нас экзамен как будет выглядеть? Просто...
Ну, вот и там и сегодня 7-й, значит, через пару недель я просто вывешу список задач. Вот и, соответственно,
То есть,
будет.
список задач на неделю?
Ну да.
Так,
Но...
экзамен, я так поняла, сдавать письменно, а вот эти вот задачи, не поздно, конечно, попросилась, вот эти вот задачи, которые просто домашка, их как
Да.
сдавать письменно?
Ну, скажем так, мне бы, конечно, было удобнее устно, вот, но если вам по каким-то причинам там...
Вообще говоря, тоже было бы удобнее устно, если я время найду.
Да, ну, в общем, ну, как вам удобнее? То есть я бы, конечно, предпочел устно, но если не получается, ну, значит, присылайте.
А про экзамен сейчас мне задавали вопросы, я сейчас уточню. Я сейчас смотрю, что спрашивали.
Марат Зефирович, там вас просят в Телеграме ответить. Короче, Влад просит.
Ну, только через какое-то время.
Хорошо.
То есть у меня часа через 2, наверное. Может быть.
Спрашивают, среди прочего, if the final will be optional, я так понимаю, что он не будет optional?
Ну, как это optional? Если сделать все задачи, грубо говоря, то... Ну, нет, ну, как бы там... Нет, он совершенно не optional. Ну просто это часть оценки, она такая, причем, я бы сказал, большая часть оценки. А что, кстати, вот интересно, что у вас, Маш, вы говорите, что у вас там что-то было, да? В каком-то видео. Это что было?
У нас, ну, собственно, у нас Вологодский Вадим Александрович, у нас была теория представлений,
Кто?
Вологодский Вадим Александрович.
Владик, ага,
вот, у нас
да.
была теория представлений, потом
Да.
мы пошли в теорию Галуа, но
Да.
мы пошли ничего не делать с бесконечными расширениями вообще. То есть
Ага.
все было доказано для конечных расширений.
Да.
И там, не знаю, я лично на семинаре пересказывал доказательства соответствия для бесконечных.
Ага.
То есть там как бы вот вычислительные задачи мы делали, там какие-то штуки для конечных расширений, которые видны для бесконечных тоже. Мы делали commerce theory была, но не была даже названа.
Ага.
И тоже как бы очень выглядящая информация.
Yeah, there is one thing we have not discussed properly, namely, do you remember at certain point we have discussed the Artin-Schreier theory? Yeah. Do you remember what's that? It's
Why complex numbers are of degree 2 over.
no. It's something different. It's also Artin and Schreier, but when I say Artin-Schreier, it's extensions, cyclic extensions. Abelian extensions of degree p of fields of characteristic p. Well, it's using roots of polynomials like x to the p minus x minus a. Yeah, so that's how p is the characteristic of the field, so you see the difference here with commerce theory, because in commerce theory you just consider arbitrary extensions, of period n, by adding roots of such polynomials, assuming that there are corresponding roots of unity. But Artin-Schreier gives you only cyclic extensions. Well, no, maybe not cyclic. Well, extensions of period p, in characteristic p. But then the question is how to construct extensions of period, say, p square. Do you know that? For that you need so of course you can say that this is not very well.
Can we just the same thing, типа x степени как на минус x степени p минус x минус h?
So can you repeat xp something like this? But the question is, there are several questions. First of all, why this it is irreducible? You see that, of course, this polynomial need not be irreducible, of course. But if it does not have a root, then it is irreducible. By the way, do you know why? Suppose that it doesn't have roots. Yeah. Why is it? Can you explain? Why is it irreducible?
С той стороны экрана говорят, что если их корень, то x плюс n тоже plane.
Okay.
X plus n.
So you mean that if alpha is a root, then is a root, then alpha plus 1 is a root as well, yeah? Okay. So what? conclusion.
Then all the elements in the field, it's irreducible in which field?
Well, it is just over some field k of x. Yeah, so it is a polynomial. So suppose that it is. Well, we just assume that it does not have a root. And the question.
So if k is infinite, then if alpha is a root, then
But
plus 1 is a root as well, and then it should have an infinite amount of roots. Then there should be a problem somewhere here.
I don't understand this. No. Yeah. So you see that we assume that characteristic is p. So what do? We can say. By the way, do you know how to express the sum of roots in terms of coefficients? Yeah. Here, but it's not. You see, it's not a problem because you know the roots. The roots are alpha plus 1, alpha plus 2, and so on, alpha plus p minus 1. And of course, if you calculate the sum, you get 0. Alpha plus alpha plus alpha. But that's not the question. The question is that if it is a product of p and q, then the sum of roots of p is what? Then the sum of roots of p is no. It just it's some number of. You see that some number of this.
You say that x is q or what?
Sure. No, it's not x. It's we assume that this polynomial is irreducible. So it is a product of two polynomials, p and q, and then we know if we know one root, then we know the all of them, yeah. And then the sum of roots of p is sum of roots of p is some multiple of alpha plus t, where s and t are certain numbers. Well, and of course we assume that p is a proper divisor. It's not a constant. It's not the whole polynomial. Yes. So and this therefore s is not 0. And this means that. So what is the sum of roots? Sum of roots is a certain coefficient. This coefficient should be in k. T is also in k. Yeah, S is also in k, because k contains. And therefore, alpha belongs to k. We check that this polynomial is irreducible if and only if it doesn't have a root.
And we think if it is reducible, then where did alpha that you were proving is in k?
You see that we can consider its well some extension of k where it has a root, and if it has one root, then we know all of them. And on the other hand, if it is reducible, it is a product of two polynomials of strictly smaller degree, then we can express the sum of root of this one of these factors as a multiple, as a non-zero multiple of alpha, and plus some element of the prime field. Okay, and this sum of roots, sum of the roots of this P is an element of our field K, because it is a certain coefficient of cosine, yeah? And therefore alpha itself is an element of K, because it's a multiple plus it's multiple by some non-zero element in prime field plus something is in K.
Why the sum of roots? Why can we see the sum of roots as
Sorry? Well, we know the roots.
Okay. Oh, okay.
So we just sum them up. Okay, yeah. So the question, yeah. So the question is, yeah. In principle, you're right. So because if we have, of course, if we have, say F, K, L. So if this is Z mod P, and so yeah. So if this is Z mod P square, then we can split it, yeah, this way. So we can consider intermediate subfield, which is so in principle you're right that you can get yes, but so let's try to do this. But you see the problem. The problem is that when you just consider extensions of yeah. So if you consider consequent. Oh, by the way, maybe I should also excuse me. I should say that if any such extension is a cyclic extension, yeah, cyclic extension of degree p, if it is. By adding the root of this polynomial, assuming that the polynomial is irreducible, gives you a cyclic extension. So it's like, well, like in commerce theory.
Потому что каждый корень это будет то, что мы добавили плюс один, и они как бы все вместе появляются, если мы один перейдем в другой, мы все будем.
Yeah, so yeah, so you can, of course, you can consider one such extension, and then again an extension of this type. But the only thing we have to know that well, actually, it's not clear whether the resulting extension will be even Galois. You see? Actually, maybe what is not really good is that we have not discussed some questions like is a normal extension of a normal extension is a normal extension again? Not necessarily, yeah? Or separable extension of a separable extension. Is it separable? So can you give an example of a normal extension of?
Okay, so let's, пусть, в общем, если альфа в четвертой это 5, то вот Q, вот если мы возьмем расширение Q, которое плюс и альфа квадрат, Q, то расширяем его до Q и альфа квадрат, ну где альфа в четвертой это 5. Типа того. Нет,
еще голос по ту сторону экрана утверждает, что пример для квадратных точек нормальных это просто, значит, это q от корня из двух, q от корня четвертой степени из двух.
Ну, вот эта задачка, она просто была в Англии.
А,
Ну да, это вроде просто... Это не просто видно, да.
okay. Yeah, so this is normal, but altogether it's not normal. Okay, and for separable,
Probability stage, I think.
it's okay, yeah. So if it is separable, yeah. So separable. Yeah. So what does it mean? It means that. Yeah, so if, what does it mean, separable?
Это any polynomial with roots in f, with coefficients in f, has a root, well, if we take a polynomial from with coefficients in f, then all its roots are in k. And правильно, вроде что любой многочлен f, многочлен z
Любой элемент является корнем сепараторным.
Сейчас. Но это тогда нужно определять, что такое сепаративный многочлен.
Сейчас. У нас получается
Сепаративность намного проще через сложение. Даже есть точное определение сепаративности через сложение.
Это что такое?
Ну, сейчас, если...
У нас было вроде такое в начале.
Если я правильно понимаю, то сепаративность это когда, если у нас есть сложение, мы знаем, что оно делает с f, то тогда у нас фиксирована область k. Или я путаю?
Я бы сказал, что это нормальность.
Нет, ну, сейчас сепаративный многочлен, это тот, который будет график подъема.
Нет. Многочлен.
Ни в каком расширении.
Ну хорошо. Хорошо, но в смысле вы имеете в виду неприводимый или?
Ну, в смысле,
Или?
сейчас говорю, если мы берем какой-то элемент из расширения, он является корнем сепаративного, ну, в смысле, его внимание многочлен, сепаративный над исходным полем, то расширение сепаративно. Среди любого элемента.
Хорошо, да, то есть, yeah, so you define separable extension as, you define separable elements, yeah? Yeah, so separable extension is such an extension that any element of this extension is separable. And separable means that its minimal polynomial doesn't have multiple roots and well, has no separable multiple. Hmm?
We can
Yeah.
say that it's coprime with its derivative.
Окей, да.
Well, you can say that its derivative is non-zero. If it is irreducible, then it's sufficient to say that its derivative is non-zero. You see that coprime and zero is the same. Not coprime and
Prime and non-zero for all elements of the extension.
yes. Okay, so so we assume that we have yeah. So in principle, yes, this is true. What else can be? We didn't discuss purely inseparable extensions, but what have we? Normal Galois.
С другой стороны
А?
экрана опять же пришло послание запоздалое. Значит, цитирую. То есть правильность утверждения верно, потому что можно определить степень сепаративности количество вложений в алгебраический замкнутое поле. Когда расширение сепаративности происходит тогда, когда его степень совпадает с
Сейчас.
сепаративностью.
Нет, это как бы, это если конечное, да, там это не работает, так не работает.
Если конечно, то конечно.
Если конечно, то да.
Ну да, нас здесь интересует бесконечное.
Ну, любые, да, тут.
А можно как-то про сепаративность понять?
Про
Если строго почему-то верно.
Почему это верно? Okay, let's try to check this. So we take an element here, and it is separable. Yeah, so it is separable over. So it is if you want a polynomial, yeah. So p at alpha is 0. So p is a polynomial over k, and p prime is not 0. Next, yeah. So we can. So what can we say now? We can, in principle, we can look at. So what do we want? We want to construct a certain to relate minimal polynomial here and here. Yeah. So there are two options: to start with this one or to start with this one. So let us call this Q. Let us call this Q. Yeah. So it's maybe it's better to start with this one.
Q is divisible by P. It's P by some elements that
Yes. So Q is minimal polynomial. Yeah. So so P is P divides Q, and what? What do we want? We want So the rest is.
Если не совпадают, то все хорошо, значит, если Q равно P, то они все параллельные. А если не совпадает, то значит в K есть какие-то корни Q.
Нет, не корни, оно просто наложение.
Ну, в смысле, ну да. Но это как-то здесь восходится с тем, что K все параллельные, да?
Actually, for me it's tempting to use differentials because it's more. I would say it's more universal, but. Yeah, so actually there are several, but actually what Vladislav says is actually it's not, it's anyway applicable here because actually we deal with finite extensions, because you see that we have to check that, what do we have to check? We have to check that.
We take the one that contains alpha as kind of extension, right?
Yes, but we have to.
So we add.
Yes, we have to replace K by the subfield generated by the. Let me remove something here. So so replace K by F, or by the subfield generated by the coefficients of coefficients of P. So this is of course finitely generated, and the L and the L by this new K of alpha. Yeah, so this is new K. New K, so this one. Okay, so then everything is finite. So we can apply these arguments, or so yeah. So of course you can use this argument with the separability degree, or use definitions like. So you know, maybe I'm not sure we have discussed this. So we have several definitions. First of all, we can say that so these differentials are zero. We can say that L over K is semi-simple. Is direct sum of fields. Yeah, is that correct? Yes. So is isomorphic direct sum of fields. What else? What are other definitions of separability? You see, actually, these are somehow related because
Вроде была теорема, что если какое-то решение является решением Galois, то оно нормально сепарабельно, а решение
Да.
Galois тогда дает пользу изложения какого-то
да.
вычисления.
Ну, это для конечных, наверное, все.
Да, но здесь у нас все конечно, да. Видите, yeah. So here we, after replacing this, we can assume that everything is finite. Yeah. So in principle, yeah. So you see that, of course, you can use this in the following way. You can try to look at conjugates of this polynomial. Yeah. So. Yeah, but but any separable, you know, that any separable extension has a Galois closure. So let me explain this. So if so maybe claim if f k over f is separable, then there exists unique up to then there exists unique up to isomorphism extension L over K such that yes. Well, it's not in a sense. Well, it is not unique in the sense that it's like, you know, that there are many algebraic closures. Yeah, but all of them are isomorphic. But so in the same sense, it is well, it is not unique, but it is unique up to some isomorphism, such that L over F is Galois, and L is the compositum. So it's minimal. It's minimal Galois extension containing containing K, compositum. Oh, and no, maybe I should write this composite. Mhm. No, and there are no smaller or proper Galois extensions. Galois are sub-extensions in L over F containing K. Yeah. So in other words, L is the compositum of sigma of K, where sigma runs over the Galois group of L over F. Yeah. So you see, just it's quite evident. You just consider all elements in K, look at their minimal polynomials, and say that L is the splitting field of these polynomials. Yeah, all of them are separable, so the splitting field is a Galois extension. Okay, and of course it is minimal. And
Wait, how do we know if L is finite? If K is finite, how do we know that was finite?
Okay, because if K is finite, then it is generated by a single element. Well, if you don't know this, you may assume that it is by finitely many elements. Yeah. And then you don't need to apply this theorem even. Yeah. You just say that it is finitely generated, and then you consider the splitting field of this finitely many polynomials. Yeah. So it's generated by finitely many elements, and you look at the minimal polynomials of these elements, and consider the splitting field, and of course it is finite. Yeah. Okay. All right. So yeah. So what can we do with this? What can we? Mm-hmm. Yeah. It is separable because the polynomials are separable, and they are separable because the extension is separable. Yeah, looks like какой-то обман, но тем не менее. Yeah, so maybe maybe we should yeah, so in principle you can argue okay. Да, правда. Yeah, so the question is, so we start with a separable extension. we look at minimal polynomials of some or all elements, and we pass to the splitting field of these polynomials, of the set of all these polynomials. And the claim is that the resulting splitting field will be separable. Is that clear?
So the question is why splitting field of separable polynomials is separable. Okay.
Yeah.
Could we improve it, please?
Yeah, maybe the problem is that we yes, the problem maybe is that we don't have some didn't stated some formal properties, yeah, of separable extensions. For instance, we did. For instance, can you show that the compositum of a system of a pair of subfields of separable extensions is separable? Yeah. So suppose we have the following diagram of fields K1, K2, F. So this is separable. This is separable. Can you show that K1, K2 is separable?
Is there a finite? No.
Well, I mean, if you want, you may assume that everything is finite because you can always reduce everything to the case of finite extensions. But the problem is that we have to choose at least one definition, yeah, of separability. But so yeah, so actually, yeah, so if we deal with, yeah, so you see that, for instance, here, these definitions work only for finite extensions, yeah.
What definition do we have for arbitrary extensions? Only with the one that says that all the elements are separable.
Yeah, or any finite any finite sub-extension is separable. Yeah. Yeah, so actually, yeah, so I think that, what can you do is that when you deal with separable extensions, you can also use the following trick. So you can, so if, let me write this way. So if we have LKF and this is separable, then differentials on L over F are just L tensor K, tensor over K of K over F. Yeah, so if
Oh, so we have, if we have the other one is separable, so then that is 0.
yes, so if this is separable, this is 0, and therefore this is 0. Yeah. Yes, yes, this is just coefficient extension. Yeah. Yeah, so the map is, well, you just, yeah, there is natural map this way, yeah. Maybe we can try to look, yeah, so we can consider the following picture. Yes, so we have, sorry, L over F. It is map, it is surjective over L over K. And the kernel is, yeah, so maybe it's better to write, yeah, so this is, what is this? L over F, and this is, yeah, so maybe over K over F, tensor K. Yeah, so okay. Yeah, so maybe it's this is more general. This is more general. Окей, ну, тогда давайте закончим действительно.
Через неделю будет?
На следующей неделе у нас планируется что-нибудь?
Наверное, или что? Или там уже какая-нибудь сессия?
Там пока ничего.
Ничего?
Еще вопрос. У нас на следующей неделе, получается, последнее занятие будет или через неделю? 21-го, видимо, или 14?
Ну, 21 будет 21 занятие?
Нет.
21-го не будет?
Нет, не будет. Это будет, ну как бы это уже будет такая, типа уже такой как бы экзамен. Ну в смысле, что?
На 14 будет.
Ну да. Ну если только